So what we're going to do is we're going to try to relate something called gravitational potential to this new concept of electric potential, because it can be a little bit challenging. Gravitational potential is a little bit easier because gravity can only do one thing. It can only attract. Whereas in electric potential, we have the opportunity to both attract and repel depending upon the charges that we're dealing with. But let's look at what gravitational potential energy is. First, it's the energy per unit of mass. So I'm just going to label as GP as the potential energy that something has per unit of mass. So potential energy is mass times gravity times height divided by mass. So in this, we get that the masses cancel out and we're left with simply GH, right? And this would be joules per kilogram of mass. Okay, so that's what it tells me. How much energy I would have G times H amount of energy per unit of mass that I have. So if we take a look at this, the potential energy of a situation where you have a mass of 10, a mass of 5, they both have a height of 3, right? The gravitational potential is G times H, so it's 10 times 3, so this is 30. They both have a gravitational potential of 30 joules per kilogram. Joules per kilogram. Okay? What that tells me is that this has 10 kilograms, right? So this is going to have 300 joules of potential energy, which is 10 times 10 times 3. And this one is going to have a potential energy of 150 joules of energy, right? And I can tell that because their gravitational potential are the same. Their gravitational potential is based on gravity, which is the same, and it's based on their location. Because they have the same height, they're going to have the same gravitational potential. Now, when they get to the ground, they're going to also have the same gravitational potential of 0. All of their energy would have been converted into kinetic, right? And if we were to drop both of these masses, they're both going to hit the ground at the same time. And so all their energy gets converted into kinetic. So what we see due to the conservation of energy is that their potential turned into kinetic. Well, remember, their potential was mass times gravity times height. Their kinetic is 1/2 mass times velocity squared. What happens here is that our masses cancel out, and how fast they're moving, the velocity, is simply 2 times gravity times height square root. Okay, so we can see that their velocity, their movement at the very end, doesn't even matter on their height. All it matters is on their gravitational potential, which is this. Their gravitational potential is really what determines how fast they're going to be moving. Another idea that we're going to review is that when they fall, there is a force pulling them down. That's their force of gravity, right? That force of gravity is equal to mass times gravity. And what we know is that there's going to be a change in potential energy, okay? And that's because there is work being done. So what we can see is that the change in potential energy is going to equal the work which is done by gravity. If we remember, work is equal to force times distance, which in this case, my distance is my height. And so my change in potential energy is going to equal my mass times my gravity times my height, okay? So for gravity, this is, again, gravitational potential right there. So what we could say is, we could say that my change in potential energy equals the mass times the gravitational potential that I have, okay? So that's a change in potential energy, and because the change in potential energy also equals the change in kinetic energy, because when I lose potential, I gain kinetic, we see that really we could also write this as a change in kinetic energy equals the mass times the gravitational potential. Okay? It is not a common way that we deal with energy because it only works in one direction. So it's a little bit easier to not really identify gravitational potential, but just use the equation mass times gravity times height when we're talking about that, right? Let's look at how this works with electrostatics. So the first thing we're going to look at is try to understand electric potential energy. And I'm not going to calculate it right now, but I just want to understand where are there high potential energies versus low potential energies within electrostatics. So if we have a positive charge here, and then we have a positive charge either at point A or point B, which one of these is a high potential versus a low potential, as well as a negative at point A and point B. So here's what we can think about. Remember, just like in gravity, right, in terms of on gravity, if we had something with a high potential energy, right, this was a low potential energy, they're both going to hit the ground at a certain speed. The low potential energy is going to hit the ground with a lesser velocity than the higher potential. So we have to think of, once we release something, what's the motion going to look like, and how much more kinetic energy could it get, okay? So A and B, which one of them is a higher potential energy for a positive charge? If we were to release both of them, which one's going to hit this charge, or which one's going to be moving faster a long time from now, right? They're both going to be repelled. This is going to move that way, and eventually it's going to speed up, right? A is going to do the same thing, but it has a much bigger force here, and it has the opportunity to speed up even more because it's been brought this close. So at this point, for the positive, this is a high potential energy. Now, potential energy, this is very specific. It's a little bit different than electric potential. This is a low potential energy. For the negative charge now, they're both attracted to this. But which one, if we would let go, would hit this positive faster? This one, even though it's a bigger force, would hit first, right? But this one has all this opportunity to speed up to this point, and then it's going to continue to speed up even more once it's here. So this is a low potential energy for the negative charge, and it's a high potential energy out there. So there's a difference between the two circumstances. What if we reverse the situation? And now we have a negative charge here, and again, position A, position B. Well, now, looking at our situation, this is a low potential energy, and B is going to be a high potential energy. A is going to accelerate here, B is going to accelerate here, and then even there, hitting the negative charge with a higher velocity. In this case, this would be a high potential energy for a negative charge, and this would be a low potential energy. So we can see that the circumstances differ. Now, energy is not a vector, and our equation for electrical potential energy is K Q Q over R. This is potential energy. It's not on our reference sheet, but it's definitely something that can be useful to understand. Okay, so what is an electric potential then? Well, electric potential, similar to gravitational potential, is now its energy per unit of charge. So that's going to be measured in what's called volts or voltage. So voltage, or electric potential, is potential energy divided by the charge. Our potential energy is KQQ over R squared divided by Q. So what we see is that one of these Q's goes away. And we're left with an equation that is KQ over R. So that is one equation for voltage. Now this is for a point charge. Those are the examples that you see here, where we have a single charge and we're looking at the region around it. So what we can see is the electric potential is based off the radius or the distance you are away. So every position that is an equal R from my charge has the same electric potential. Now here's some special things with this. These electric potential lines are always perpendicular to my field lines. Maybe not drawn perfectly, but they're supposed to be. Okay? These are called equal potentials. They're called equal potentials because every place on here is maybe 10 volts. 10 units of energy, 10 joules per coulomb, right? So it's measured in volts, which is joules per coulomb, right? Energy per charge. Okay? If we were to go further out here, this would be a smaller potential because I have a bigger R. This might be 5 volts. Closer might be 15 volts. Right? Around the negative, we're going to have a similar. However, because this is a scalar, it's not a vector. Right? Here would be negative 15 volts, negative 10 volts, and so on and so forth. The voltage or the potentials here are negative, whereas around a positive, they're going to be positive. So there could be a point in between them where our electric potential is 0. Right? If we had a positive and a negative, we go with 15, 10, 5, 0, negative 5, negative 10, negative 15. And you see that in the lab that you're working through. Now, the last thing that I want to point out in this video is just what are positive and negative charges going to do in comparison to the electric potentials that they're in. So if we have a positive charge here, that positive charge naturally wants to fall, just like this, if I drop it, naturally wants to fall. It wants to fall this way, right? If we had a positive charge here, it naturally wants to fall this way. It wants to be repelled from this. So what we see is that we see a positive charge move from high potentials to low potentials, from 15 to 10 to 5, to 5 to 2 to 1, and so on and so forth. Is that still true here? If we have a positive charge here, it naturally wants to move this way. Well, this is a scalar. Negative 10 is bigger than negative 15. So what we see is we still see a positive wants to move from a higher potential to a lower. It wants to go from negative 10 to negative 15 to negative 20. What about a negative charge? We'll put a negative charge here. Negative charge naturally is attracted to the positive, so it's going to move from 10 to 5. All right? Well, what if we put it out here at 15? Or excuse me, pardon me. It's going to move from 10 to 15. Sorry. What if we put it out here at 5? That negative charge wants to naturally move this way, from 5 to 10 to 15. So what we see is we see negative charges move from low potential to high. Is that also true here? If we put a negative here, it's repelled. It naturally wants to move this way. So it's going to move from negative 15 to negative 10. That's going to a higher potential. Okay? If we were to start a negative 1 out here, it's going to move from negative 10 to negative 5 to negative 2, and so on and so forth. So these are the two things that we need to make sure we understand, that naturally what happens, positive charges move from a high potential to a low, just like gravity, right? This is a higher potential, it naturally wants to move to a lower potential, right? Negatives are opposite. It'd be like anti-gravity, right? If we had something down here, it naturally wants to move up. If we have a negative, they move from a lower potential, electric potential, to higher electric potential. Not energy, but low potential to higher potential. Right? Our next video, we'll go through a little bit more of how we can apply this, as well as looking at what the electric potential looks like in a uniform electric field or within a capacitor.